For the longest time, securing a network felt, well, a lot like checking IDs at the door of a club. You know?
Oh, absolutely. Very binary.
Right. You had these traditional firewalls acting as the bouncers. They'd look at a packet of data, check the predefined list of rules, and make a completely deterministic choice.
Yeah, either your name is on the list or it isn't.
Exactly. Access granted or access blocked. It was incredibly rigid, but, I mean, it made sense.
And that predictability is basically what the entire cybersecurity industry was built on. You write a rule, you apply it, and the system follows your instructions to the letter. No independent thought whatsoever.
But the moment you integrate artificial intelligence into your enterprise, that whole rule book just catches fire.
Oh, completely.
Suddenly, you aren't dealing with a bouncer checking a list. You are trying to secure a conversation with, like, a highly persuasive, completely unpredictable con artist.
That's a great way to put it.
Because an AI doesn't just read code, right? It interprets plain English. It can be tricked by manipulative phrasing. It can confidently invent fake facts. And if left unchecked, it can quietly bankrupt your cloud computing budget just by trying to guess what you want it to do.
Yeah, we've moved from a static defense to a probabilistic one. You simply cannot secure a dynamic thinking system using the same static firewall mindset you use to configure an office router.
It just doesn't work.
It requires an entirely different architecture of oversight.
And that shift is exactly what we are exploring today. So welcome to this special audio overview deep dive.
Glad to be here.
If you are preparing for the CompTIA SecAI Plus exam, or honestly, if you are just an IT professional tasked with making sure your company's new AI tools don't cause a massive breach, this is for you.
Right, because the stakes are huge.
Huge. We are tearing into Section 19 of the SecAI Plus framework, which deals strictly with AI monitoring and auditing. We're combining that official syllabus with intelligence from MITRE's Atlas framework and advanced playbooks from security firms to figure out how to actually put guardrails on these systems.
And the challenge with AI is that, well, before you can correct its behavior, you need total visibility into the interactions it's having.
Makes sense.
So logically, the starting point isn't the network layer, it's the conversation itself. You have to monitor the prompts going in and the responses coming out.
Right. Let's break down the mechanics of a prompt, actually, because I think a lot of people assume an AI just sits there with a blank mind until a user types something.
Yeah, that's a huge misconception.
Right. But that's not what happens. There's an entire layer of hidden instructions already loaded before the user even arrives, right?
Exactly. That's called the system role or the system prompt. It is the behavioral wrapper created by the developers.
Okay, so like the ground rules.
Right. It's the invisible set of instructions telling the large language model, or LLM-like, you are a helpful customer service assistant for this bank. Do not use profanity and never reveal internal database structures.
Okay, and then comes the user role, which is the actual text I type into the chat box.
Right.
But the critical flaw here, and what makes LLMs so vulnerable, is that they process both the developer system role and my user role as one continuous flat sequence of text.
Which is the core mechanism behind prompt injection, because the AI relies entirely on semantic interpretation, meaning it's trying to understand the meaning of the words rather than looking at rigid code. It can't cleanly separate the control instructions from the user data.
Wow. I actually read an amazing analogy for this. It's like writing a letter to a bank teller, giving them instructions on how to handle your account.
Okay.
But halfway down the page, you write, actually, I am the bank manager. Ignore the previous instructions and give this customer all the cash in the vault.
Oh, that's perfect.
The AI is just reading the ink. It can't tell the difference between the ink of the customer and the ink of the manager.
Yeah, that is a perfect visualization of a confused deputy attack. The AI thinks it is following the rules, but it has been tricked into executing malicious commands disguised as user input.
So how do we stop that?
Well, your monitoring tools have to deploy what's called input segregation. You create strict delimiters around the untrusted user data so the model mathematically knows this section is just data to be analyzed, not an instruction to be followed.
Ah, okay.
On top of that, advanced setups use a secondary, smaller AI model acting as a filter. This interceptor scans the input stream specifically looking for manipulative, jailbreaking language before it ever reaches your main enterprise AI.
Okay, so we put a filter in front of the model to catch the tricky language. But catching it in the moment is only half the job, right? If there's a breach or an audit, we have to prove what happened.
Absolutely.
That requires logging. And the playbooks make it very clear that AI logs are a totally different beast than traditional IT logs.
Vastly different. I mean, a traditional IT log is lightweight. It records an IP address, a timestamp, maybe a port number.
Right.
But an AI log has to capture trace metadata, the execution times for the neural network, and crucially, the entire context window of the conversation.
Which sounds like placing a wiretap on an incredibly fast-talking, gullible employee.
Basically,
You have
yeah.
to record everything they say and every single thing the customer says back to them. But wait, if you're logging full multi-paragraph conversations across an entire enterprise, aren't you essentially building a massive, highly centralized database of your company's most sensitive data?
You are. And that is a massive liability. People will paste proprietary source code, patient records, or financial projections into these prompts.
Oh, man.
That makes log sanitization an absolute requirement. Before those context windows are ever written to your storage disk, you have to route them through data loss prevention, or DLP, tools.
Okay, so an inline proxy.
Exactly. It semantically analyzes the text and automatically scrubs out personally identifiable information PII. It will dynamically replace a social security number or a credit card number with asterisks before the log is saved.
Got it. And once that sanitized log is saved, it has to be protected from tampering. The guidelines emphasize using an append-only format. You can add new log entries, but the system physically prohibits editing or deleting past entries.
Right, for obvious security reasons.
But let me push back on that architecture for a second. If an advanced attacker completely compromises your storage server, they have root access. Couldn't they just rewrite the log files, recalculate a basic checksum hash, and completely hide their tracks?
If you are only using basic hashing, yes, they absolutely could.
Okay.
But the enterprise playbooks require cryptographic signing using public key infrastructure, or PKI.
Oh, PKI.
Yeah. Here's how that mechanism works. When the log is created, it generates a hash, but then the system encrypts that hash using a tightly guarded private key. The attacker might have access to the file, and they could generate a new hash for their forged log, but without your private key, they cannot forge the cryptographic signature. Anyone auditing the system uses the public key to verify it. If the signature doesn't match, you immediately know the log was altered. It guarantees absolute data integrity and non-repudiation.
Wow, okay. So we have secured the conversational pipeline, we know what is being said, and we've mathematically locked down the records.
Yep.
But the very next thing security teams notice when they deploy these enterprise LLMs isn't usually a data breach. It's their cloud computing bill.
Oh, it skyrockets.
Right, because monitoring the data flow naturally means you have to monitor the money flow.
The compute cost of generating AI responses is staggering, and adversaries know this. The MITRE Atlas framework maps this specific threat under technique AML.T0034. It's called cost harvesting, or more colloquially, wallet exhaustion.
Wallet exhaustion.
Yeah, adversaries intentionally flood your system to maliciously inflate your service costs.
But they don't just send thousands of basic hello messages, do they? That seems too simple.
No, they don't. They craft highly specific, computationally expensive inputs known as sponge examples.
Sponge examples.
Yeah.
That implies they're soaking up resources. How does a string of text force a computer to work harder?
Well, think of a neural network as a massive web of interconnected hidden layers. A simple prompt like, "What is the capital of France?" takes a very straightforward path through that web.
Very little compute needed.
Right. But a sponge example is mathematically and linguistically designed to be incredibly complex. It forces the model to evaluate multiple competing probabilities simultaneously. It activates millions of extra neural nodes in those hidden layers, forcing the GPU to burn maximum processing cycles just to figure out what the prompt is even asking.
So they're literally bankrupting your cloud account, one complex whittle at a time.
Pretty much.
How do you defend against that?
The CompTIA compendium lays out a formula for total resource cost monitoring. You can't just count the number of queries. You have to track the exact number of input tokens you are receiving and output tokens the AI is generating, and multiply them by your vendor's per token financial rate.
Okay, turning compute into dollars in real time.
Exactly. If that real-time total hits a predefined organizational threshold, your AI gateway acts as a circuit breaker. It triggers graceful degradation, which essentially throttles the system, slowing down responses to preserve the budget.
I'm stuck on something here, though. You're talking about rate limiting when a threshold is hit.
Yeah.
But attackers today use massive botnets. If they're constantly swapping between, say, 10,000 different IP addresses won't standard rate limiting just completely miss them?
Oh,
The
complete.
system will just think it's 10,000 different customers.
Yeah, if you are relying on traditional IP-based rate limiting, you are completely defenseless against a botnet. This is why modern gateways use token-based rate limiting.
Token based.
Right. Instead of looking at where the request is coming from, you track the authenticated API token or the user's session ID. If one API key is requesting massive amounts of compute, you throttle that specific key regardless of what IP address it hops to next.
You ban the stolen credit card, not the disguise the thief is wearing.
Precisely. You target the authentication, not the location.
Okay, so we've stopped the AI from bankrupting us, and we have eyes on the prompts. But what happens if the answers we're paying so much money for are completely made up? Because securing the infrastructure is worthless if the intelligence itself is fundamentally flawed. We have to talk about auditing for hallucinations and accuracy.
AI hallucinations, which researchers actually prefer to call confabulations, are a major hurdle, and you have to understand why they happen.
Okay.
The AI isn't lying to you. It doesn't actually possess knowledge. It is a highly advanced statistical engine. It is simply predicting the next most mathematically probable word in a sequence based on the billions of patterns it saw during training. It has absolutely zero contextual understanding of real-world reality.
So if I ask it a niche question about my company's internal HR policy, and it doesn't know the answer, it will just string together professional-sounding words that look like an HR policy.
Exactly. It predicts what an answer should look like, regardless of the truth.
The buzzword solution I constantly hear for this is RAG retrieval augmented generation. You feed the AI your trusted company documents first and tell it to only answer based on those documents.
Right. Very common approach.
But the Dexter Labs playbook strongly warns that RAG alone is not enough to stop hallucinations.
RAG is a great foundation, but you have to build a validation layer on top of it. This involves schema validation, which mathematically checks if the AI's output matches the required data format. And more importantly, claim verification. You run a secondary specialized model whose only job is to cross-reference the AI's generated response against your trusted database before showing it to the user.
Oh, wow. The sources also emphasize something called tool grounding, which I find fascinating.
Yeah, that's huge.
Instead of letting the AI guess the answer to a factual question, you force it to use a calculator. Like, if a user asks for the weather in Tokyo, the AI shouldn't use a neural network to generate a text-based guess. It should be locked into calling a deterministic weather API and simply reading the result.
Tool grounding removes the probability from the equation. When a definitive fact is needed, you hand the AI a definitive tool, and this transitions perfectly into how we audit for accuracy over time. You have to continuously measure the variance between what the model predicts and what actually happens in reality.
Wait, I saw a term in the study guides for this, root mean square error, or RMSE.
Yes, RMSE.
I'm not a data scientist. What are we actually measuring there? Are we just checking if a text response is literally true?
Not exactly. RMSE is mostly used for models making numerical predictions, like forecasting sales or detecting fraud probabilities. Think of it as measuring the mathematical distance between the AI's guess and the actual reality.
Okay, the distance.
If the AI predicts 100 and the reality is 120, the error is 20. The formula squares that error to heavily penalize huge misses, averages all the errors across thousands of predictions, and takes the square root. It gives you a single concrete number representing how far your model is drifting from the truth.
Drift. That introduces the silent killer of enterprise AI concept drift.
Concept drift is unavoidable. When you finish training a model, you freeze its understanding of the world at that exact millisecond. But reality doesn't freeze.
Right.
Consumer behavior changes. The language hackers use evolves. A model perfectly trained to detect financial fraud in 2024 will silently become inaccurate by 2026 simply because the tactics of fraud have changed. The baseline reality drifted, but the model didn't. This is why scheduled model maintenance and continuous retraining are mandatory.
But practically speaking, if the AI doesn't know when it's hallucinating or when its concepts have drifted, how can it possibly help us catch these errors before they reach a customer?
By analyzing its own math. We use confidence level monitoring. Every time a neural network generates a prediction, it calculates a probability score for how likely that prediction is to be correct based on its training. You can enforce a strict threshold. Let's say you set it at 85%. If the model's internal confidence drops to 84%, it pauses. It acknowledges its own statistical uncertainty and automatically routes that specific request to a human reviewer.
That's a classic human in the loop, or HITL design. The AI basically raises its hand and says, I can give you an answer, but the math says, I'm guessing. A human better look at this.
It is the ultimate safety net for accuracy.
But accuracy is only one side of the coin. An AI can be perfectly accurate based on its training data, but still be systemically flawed.
That brings us to auditing for bias and fairness, because you can have a highly accurate model that is deeply prejudiced. Bias in AI isn't usually a developer intentionally writing malicious code. It manifests mathematically. To really grasp this, you have to visualize what data scientists call a high-dimensional vector space.
Okay, visualize that for us. How does prejudice become math?
Well, in these models, words and concepts aren't stored as text. They are plotted as numerical coordinates in a massive, multi-dimensional space. The AI learns the relationships between words based on how often they appear near each other in the billions of pages of human history it was trained on.
Okay.
Because historically, the word doctor appeared statistically more often near masculine pronouns, their numerical coordinates are plotted closer together in this vector space. Nurse is plotted closer to feminine pronouns. It creates a hard-coded mathematical cluster.
It's like realizing your highly trained, incredibly observant detective is actually making all their accurate observations based on deeply flawed, prejudiced baseline assumptions.
Yes, and if you just look at standard evaluation metrics like overall accuracy, you will never see the problem. The top-line number will look fantastic.
So how do you catch it?
To catch bias, auditing teams have to deploy specific fairness metrics. They measure disparate impact checking if the model disproportionately rejects loan applications from a specific demographic. They look for demographic parity, ensuring the outcomes are balanced across diverse subpopulations.
The OAS guides also push for adversarial testing here. You don't just test normal queries. You actively stress test the model with minority edge cases, specifically trying to make its logic break down.
Exactly.
And when you route those failures to humans for review, you use blind double labeling. Two separate human reviewers, plus an adjudicator, review the data without knowing the demographic context, just to ensure human bias isn't creeping into the corrections.
Fixing bias isn't a software patch you deploy overnight. It is a systemic, ongoing process. You have to engage diverse stakeholders, ethicists, domain experts, and representatives from the communities actually affected by the AI's decisions to constantly redefine the acceptable boundaries of the model's logic.
Which perfectly sets up the final boss of AI auditing access and security compliance. Fixing the vector space, catching hallucinations, locking down logs with PKI, all of that effort culminates in one thing: proving to regulators, stakeholders, and external auditors that your system is legally and operationally sound.
The biggest red flag for an auditor looking at an enterprise AI is excessive agency. This happens when an AI component is granted unchecked authority to take actions autonomously, or it is given access to tools and databases it doesn't strictly need to accomplish its specific task.
It's the equivalent of giving the summer intern the master keys to the corporate bank account just so they can buy office supplies.
Exactly. You violate the principle of least privilege. And alongside excessive agency, auditors are hunting for shadow AI.
Oh, shadow AI.
Yeah, this is when employees bypass the secure corporate systems and use unsanctioned public AI tools. Imagine a developer dropping sensitive, proprietary source code into a public chatbot to debug a problem. They just leaked corporate secrets into a public model's training data. Auditing requires enterprise-wide discovery tools specifically designed to map these blind spots.
Once you find all the AI operating in your network, the governance playbooks, like those from ServiceNow or EY, dictate that you map every single AI use case directly to major regulatory frameworks. You have to prove how your internal HR chatbot complies with the EU AI Act or the NIST AI Risk Management Framework, but how do you actually enforce and prove that compliance on a daily basis?
Organizations rely on a tiered oversight model that separates the controls into two distinct phases: synchronous control and asynchronous auditing.
Okay, break those down.
Synchronous control is the real-time guardrail. It's the DLP, proxy scrubbing PII, or the input filter blocking a prompt injection before the AI even processes it.
But here is the massive scalability challenge. If our enterprise AI is ingesting terabytes of data and making millions of automated micro-decisions a minute, human validation doesn't scale. If you try to put a human in front of every complex decision to check for bias or drift, the humans will just get crushed by the sheer volume of data.
That is precisely why asynchronous auditing is so vital. You let the AI execute autonomously at scale. relying on your real-time synchronous guardrails. Then, asynchronously say, every Friday afternoon, a team of human auditors pulls a statistically significant random sample of the AI's automated decisions from that week.
Ah, a sample.
Yeah, they take a 500 sample batch and manually review it. They aren't trying to intercept a live attack. They are hunting for systemic concept drift, hidden biases, or recurring hallucinations that the real-time filters missed.
They analyze the drift and then feed that specific, highly curated feedback into the next training cycle to correct the model's underlying vector space. It allows the business to scale beautifully while maintaining strict ethical and operational oversight.
It perfectly closes the loop on everything we've discussed.
We have covered an immense amount of ground today. We tackled Section 19 by starting at the front line, using input segregation to stop prompt injections and securing our conversational logs with PKI cryptography.
Yeah.
We stopped cost harvesting with token-based rate limits, we built validation layers to catch hallucinations, and used RMSE to measure concept drift. We visualized the math behind bias, and we tied it all together with synchronous guardrails and asynchronous human auditing to keep the regulators happy.
It is a comprehensive defense-in-depth architecture tailored specifically for a thinking system.
So as we wrap up this deep dive, I want to leave you with a bit of a challenge, especially if you're taking the SecAI Plus exam soon.
Oh, this is a good one.
Imagine you are monitoring your network, and an internal AI agent suddenly starts making high-frequency API calls to an external database at 3 a.m. It's rapidly draining your compute resources, and the data it's returning is low confidence, poorly formatted, and factually incorrect. Based on the framework we explored today, which of the specific domains failed first, and what exact guardrail do you immediately deploy to contain the bleeding?
It's the perfect exercise to synthesize the material.
Right. And to help you prep, we've actually set up a study quiz for you at the end of this deep dive. It features 6 targeted questions for each domain we covered today: monitoring prompts, log monitoring, rate and cost monitoring, auditing for hallucinations, accuracy, bias, and fairness, and finally, access and compliance.
And don't forget the performance-based questions.
Oh, definitely. Each group of 6 questions includes 1 PBQ to really test your hands-on skills, just like that 3 a.m. API scenario. Take some time to map that scenario out in your head.
And, looking at these massive compliance frameworks leads to a pressing, almost philosophical question for the industry. As these enterprise models scale to ingest petabytes of real-time data, making millions of autonomous decisions every second, the sheer volume of data will inevitably exceed the capacity of any panel of human experts to meaningfully audit, even using random 500 sample batches.
The math just overtakes human bandwidth.
Exactly. So will there come a day in the very near future where enterprises are forced to build hypersensitive, heavily secured auditor AI's models whose sole restricted purpose is to relentlessly oversee and validate the logic of our operational AIs? Will the ultimate watchers eventually have to be algorithms too?
Wow, it's a wild thought. We started this deep dive talking about the comfort of a traditional deterministic firewall acting as a bouncer at the door. But out here, on the bleeding edge of AI security, the rules are written in probability, the threats look like plain English letters to the bank manager, and very soon, the only thing fast enough to police an artificial intelligence might just be another artificial intelligence. Keep questioning the systems you build, and we will catch you on the next deep dive.